Hello everyone, I'm Norbert Marburger. Today we're going to look at the sociology of going to infinity. And we're going to apply some basic logical reasoning to, well, largely kill number theory. We're going to do that by showing that if you accept the rather unwarranted assumptions, from my point of view, of modern analysis and number theory, that in fact you can basically solve almost all famous number theoretical problems basically at the drop of a hat. And I'm going to exhibit this in the context of one particular problem, but the argument is actually quite general, and it's an interesting exercise for undergraduates or graduate students to simply convert the argument that I'm showing you today to solve basically any other important open number theory problem. So we're going to look at the twin prime conjecture, which asks whether there's an infinite number of twin primes, that is, primes which are exactly two apart. And what I'm going to suppose is that I am in possession of what all my mathematical peers assume they are in possession of, namely an ability to do an infinite number of things. So for example, cosine of 7, that's an infinite series, and to assert that there really is such a number is essentially to assert that you're able to do this infinite number of arithmetical operations and get a bona fide result at the end of it. Not just cosine of 7, but say zeta of 5, the zeta function. 1 over 1 to the 5 plus 1 over 2 to the 5 plus 1 over 3 to the 5, etc. to infinity. Right? It's a staple of number theory. That's an important function that tells us a lot about prime numbers. And it really does make sense. There really is such a thing as zeta of 5, which is what you get when you add up all these infinite number of things. So that's the position I'm going to take. That's not my ordinary position, but just for the sake of this particular talk, I'm going to assume that I have these Superman powers along with my fellow mathematicians. And let's solve the twin prime conjecture, shall we? So without even using the blackboard, I'm just simply going to explain an algorithm. Okay, we're going to compute a number. We're going to compute a number which determines the truth value of this proposition that there are an infinite number of twin primes. Okay? So just a little bit of programming is all that we'll need. We're going to start with a total. The total is currently 0. So there's a box called total. We're putting 0 in there, and we're going to add stuff to that. Okay? And what's in that total box at the end is going to be the thing that really interests us. Okay, we're going to start with the number 1. We're going to work our way through the natural numbers. Actually, since we're looking for twin primes, it'll suffice to just go through the odd numbers, okay? And we're going to be searching for when we get a twin prime pair. So let's start with 1. Well, 1 is not a prime generally considered, so 1 and 3, that's not really a twin prime pair, so that doesn't give us anything. The next odd number is 3. And then 3, and the next one is 5. Ah, that's a twin prime. We found our first twin prime pair. So over here we have a counter, okay, which we're going to set to 1 because we found the first twin prime pair. So our twin prime pair counter is equal to 1. And consequently, I'm going to change the total. I'm going to add to the total 1 over 2 to the twin prime counter. So 1 over 2 to the 1. So now the total has a total of a half in it. Excellent. Okay, now we're going to augment our odd numbers to 5 and ask, 5 and 7, is that a twin prime? It's easy to calculate that, right? If we're able to do an infinite number of things, we can certainly calculate whether any given number is prime. That's done in a snap. And 5 and 7 are both prime. So hey, there's another twin prime pair. So our twin prime pair counter goes up from 1 to 2. And since it's just been augmented to 2, it means we have to augment our total. We're going to add to our current total 1 over 2 to the 2. 2 because of our twin prime counter having the value of 2. So now in total we have 1/2 plus 1/4, which is 3/4. Okay, the next one is 7 and 9, that's not a twin prime pair. 9 and 11, that's not a twin prime pair. 11 and 13, that's a twin prime pair. Okay, no, twin prime pair. So our counter, twin prime pair counter, goes up from 2 to 3. And we're going to add to our total 1 over 2 cubed. And we're going to carry on like this. So the total, what's going to happen to the total? At each stage, we're adding the next reciprocal 1 over 2 to the k, if at all. Okay, if something is being added, it's 1 over 2 to the k, where k is 1 more than the previous one. And such an addition happens every time we find a new twin prime pair. And so now, ladies and gentlemen, we are going to go to infinity. As my analyst friends do all the time, as my number theoretical friends do all the time, as my algebraic geometer colleagues do all the time. We just go to infinity. We we assume that we can just carry this computation out to the end. To the end. Are we all in agreement that we can do that? Yes, we're all nodding. We have beatific smiles. We are pure mathematicians. We stride across the universe of thought. So we have gone to the end of this algorithm. Okay, so let's have a look what's in this total. Well, if there's only a finite number of twin primes, then what's in that total is going to be a rational number which is strictly less than 1. It's between 0 and 1. So the form 1/2 plus 1/4 plus 1/8 plus 1/16, etc., up to some 1 over 2 to the value. However, if there are an infinite number of twin primes, then we will have gone through the entire series, 1/2 plus 1/4 plus 1/8 plus 1/16, etc., to infinity. And we all know what that sums to. It sums to 1. So in our final step, what we're going to do is we're going to take that number total, and we're going to take the greatest integer part of it. That means that if it's an integer, it stays an integer. If it's something like 2.7, the greatest integer part is 2. If it's 0.89, the greatest integer part is 0. So we take the greatest integer part of this total, and we're either going to get 0 or 1. That's the result of a calculation. And in principle, it's not really so different from a calculation like cosine of 7 or zeta of 5. It involves an infinite number of arithmetical steps, each of which is reasonably completely clear. It's just that as we go further and further, the numbers involved get bigger and bigger. In practice, of course, eventually they get so big that they don't fit into the universe, but that doesn't bother our analyst friends. They just pretend that you can still do these arithmetical infinite computations, and we are going to follow that route. So this total that I've obtained is a completely legitimate object. It is either 0 or 1, whatever is in there, and that is the truth value of the proposition that there are an infinite number of twin primes. So I have solved that conjecture here for you today, completely computationally. It's a computation that we have made in the same way that one calculates or talks about cosine of 7 or zeta of 5 or any number of other such transcendental functions in mathematics without even a qualm, without even the slightest hint of embarrassment. So of course this elevates me to a very high status in the world of number theory now, especially once a little bit of thought is applied. You see that basically the same argument can, or a very similar one, can be used to solve pretty well every famous number theoretical problem. And so this is a great exercise to go ahead and solve some famous problems. You can become famous this afternoon. Just write out exactly a parallel kind of argument for your favorite number theory problem, and then you will be credited forever after with having solved that problem by pure thought. In my next video, I'm actually going to apply the same reasoning to the most famous unsolved problem in mathematics. And let's see if we can crack the Riemann hypothesis. I'm Norman Wildberger. Thanks for listening.